So, welcome back to this class on hardware security. So, we shall be continuing our discussion on finding out the compact AES S box for normal basis representation. So, if you remember in the last class, we were essentially stopped at the scaling and squaring optimizations, and we will continue from that point. Okay. So, this is a quick recapitulation of the normal GF2 power of 4 squared inversion circuit, where we were able to decompose my GF2 power of 4 square circuit in terms of GF2 power of 4 computations. So, for example, the multipliers are now in GF2 power of 4, the inversion is also in GF2 power of 4, and likewise the scaling and multiplication, there is a scaling operation where you are multiplying with the mu, which is a constant, is also in GF2 power of 4. Okay. So, we shall try to see how these individual components can be now worked out. We already worked out the product in GF2 power of 4, right, essentially where we were able to do multiplication in GF2 power of 4. The idea was that we will write an element in GF2 power of 4 as GF2 power of 2 whole power of 2, and therefore continue our operations from there. Okay. So, now when we see that when we work out this GF2 power of 4 multiplication, then we have got several multiplications which are now in the subfield GF2 power of 2. Okay. So, we should be able to work that also out. And here is a way how we can do that. When you are doing multiplications in GF2 power of 2, you can isomorphically write it as an element in GF2 power of GF2 power of 2. That means, right, there are two parts now in the representation. That means, when you are multiplying two elements, say your elements are gamma and delta. So, gamma is an element in GF2 power of 2. Okay, and so when you are doing this multiplication, right, is that when you essentially these are your corresponding arguments which you are multiplying. Okay. So, for example, if you go back and see the equation here, then when you are doing this multiplication in GF2 power of 4, then these elements, that is gamma 1, gamma 0, are in GF2 power of 2. Okay. So, therefore, right, likewise delta 1 and delta 0 are in GF2 power of 2. So, now you need to do these computations like like for example, gamma 1 delta 0, that means you have to multiply in GF2 power of 2. So, how do you do that is shown here. That means, I take two elements in GF2 power of 2 and I show how to do a multiplication. So, I take a gamma which is in GF2 power of 2, I take a delta in GF2 power of 2 and then I multiply them. So, again when you are essentially like having an element in GF2 power of 2, that means if you consider an element say like in GF2 power of 2, so that means, right, your element has got two parts again, okay, and each of these elements are now in GF2. So, this element is in GF2, this element is also in GF2. So, for example, one element is a G1 denoted here as G1 and the other one is G0. The basis of this is W square and W. Okay. So, therefore, my element is G1 W squared plus G0 W. Likewise, my other element is D1 W squared plus D0 W. So, when I am multiplying them, right, essentially I get these elements, I get G1 D1 plus like I essentially I am just doing the individual multiplications, and note that I also have this equation, that is W square plus W plus 1 is equal to 0. Okay. So, essentially I will try to use this as my tool for simplification and bring the result back in the original field. Okay. So, once you have done that, then you essentially get your result back in the original basis, that is omega squared and omega, and these are your corresponding output coefficients. Okay. So, if you understand this, and I leave it to you as an exercise to work out the details of how essentially you can simplify and bring the result back into W square and W. Okay. So therefore, right, I mean so if you have understood this, right, then we can continue further and see how the next computations can be done. For example, the most important step, as I was mentioning, is the squaring and the scaling operation in GF2 power of 4 squared. So, note I am doing a scaling with mu. So, mu is my constant, which is denoted as delta 1 z power of 4 plus delta 0 z. Okay. And I am applying this scaling on the square of gamma. Okay. So, the gamma is essentially nothing but gamma 1 z to the power of 4 plus gamma 0 z. Okay. So, this step is essentially this blocks. Okay. This box, that is, this box is what we are now trying to expand. Okay. So, if you now want to get into the details, then that means that when you are doing a gamma square, so note that gamma is nothing but gamma 1 z power of 4 plus gamma 0 z. That means gamma square essentially can be written in this form. Okay. So, again I am not going into all the details about how this squaring can be done, but again like leave it to as an exercise to verify, because we have already worked out this product, right, where we have multiplied, for example, where we essentially have done this multiplication. So it's just a simple case where the squaring is nothing but a multiplication where two inputs are exactly same. Okay, so if you plug into that, right, you should get these equations. Okay, and exact details I again leave it to as an exercise. But interestingly, we look into the scaling operation, the scale and squaring operation. Okay, so when you are doing a scaling and squaring operation, that means you are now multiplying with this constant, which is delta 1 z power of 4 plus delta 0 z, with this output, and this is essentially nothing but the squared result. Okay, again if you do a few more manipulations, then you will see that there are two terms here, again one which is essentially can be expressed in z power of 4 and z, and these are the two components. Okay, so one component is shown here as like, so this is my like one component. Okay, and the other component is this, and you can see that the basis is z power of 4 and z. So again I have written the result of doing a scaling and squaring in my field. Okay, because I have been able to express that in the original field. So now with this, right, we essentially can observe few more interesting things. Okay, so to start with, when you are doing this optimization and I want to do further more optimizations, let me set delta 1 is equal to n delta 0. Note that the choice of mu is in my hand to some extent. Okay, so if I plug in this optimization, that is delta 1 is equal to n delta 0, then you can observe that this mu gamma squared essentially had this was my original equation, but then you can observe that this term will vanish, because delta 1 plus n delta 0 because of this optimization will work out to 0. Okay, so therefore, right, this will get simplified into this form, where you have got you have got delta 0 squared multiplied with n gamma 0 squared multiplied with n delta 0 z power of 4 plus this part. Okay, so now you note that since delta 1 is equal to n delta 0 and I plug it over here, I get n square delta 0. Okay, so now if I take delta 0 common from here, I will have got 1 plus n squared, and note that again n square plus n plus 1 is equal to 0, and therefore I can substitute 1 plus n square with n. Okay, so therefore this is my final form. So note that if I want to do this computation, I have to do two scaling operations. One is a scaling with n, scaling means multiplication with a constant in the lower field, and another one is a squaring with n square. So these are my two scaling operations that I need to do, and I have to do one more addition. So I have to do one addition here, then that's enough. Okay, note that the squarings in GF2 power of 2, because there are some squarings which you are doing, but now these squarings are is the lower field GF2 power of 2, okay, GF2 power of 2, and that is free. Okay, as I have already kind of hinted to you in the previous discussions. Okay, so therefore, right, you essentially have a pretty compact form of the squaring and the scaling operation. Okay, although it is not totally free. Okay, so therefore, but at the same time it is pretty easy to observe. For example, right, in order to see that the squaring is also free, you can easily work that out. So suppose my input is G1 W square plus G0 W. So again this is missed out. So you can just correct it by writing this G0 W. So if I do a squaring operation, then I can work this out as G0 W square plus G1 W. Okay. So note that if this is my input and this is my output. Therefore the squaring can easily be done by just doing swapping of the inputs. So you just need to do a swap and you will get the corresponding output without any explicit computation. Okay. So now with this, right, we should be able to understand how so now we can again take a look at the lower or the GF2 power of 4 inversion. Again it can be worked out exactly in the same fashion like what we have seen previously, but now my computations are, or the sub computations are in GF2 power of 2. Okay. So the circuits for squaring and scaling in GF2 power of 2 can be simplified by assuming the choices of n, which can be either W or W square. Okay. And depending upon that, you probably have to do a scaling with W or a scaling with W square. Okay. So in both cases, you can see that whether you are doing a scaling with W or whether you are doing with scaling with W square, you essentially have got similar computations which are required. Okay. So therefore, in one case, it is just like G1 plus G0 W square plus G1 W. In the other case, it is G0 W square plus G1 plus G0 W. Okay. So this is how you can do the this part where you are basically doing a scaling with n. Okay. So finally, right, we essentially have derived all the individual steps, and just for completion we now need to do the final transformation, both from GF 2 power of 8 to GF 2 power of 2 power of 2 and from this field back to GF 2 power of 8. So we present like in the polynomial basis another way of doing this mapping. So we take an element, say G, which belongs to GF 2 power of 8, which is a standard AES representation. You can abbreviate it from by the tuple from G0 to G7, and therefore this is your corresponding polynomial representation. In the normal basis, when you are mapping this to say B7 to B0, then you note that this element, that is when you are expressing it as GF 2 power of 4 squared, will have two parts. Okay. The first part is say gamma 1, second part is gamma 0. So my element is gamma 1 y power of 16 plus gamma 0 y. Likewise, these gamma elements are elements from GF 2 power of 2 whole power of 2. So I can express them as say capital gamma 1 z power of 4 plus capital gamma 0 z, okay, and likewise. So therefore, right, what I can do is now, that means each, and furthermore each of these elements like gamma will be an element in GF 2 power of 2. So therefore I can write that as d1, like I can write this as d1 or b1 w square plus b0 w, okay, where each of these b1 and b0 are my bits, are in 0, 1 values. Okay. So bringing all of them together, that means this polynomial is nothing but, there are two parts. You can actually, like in the equivalent, in the converted form, actually you essentially have these two parts, right. For example, when I am having, this is my higher part and this is my lower part. So you see that I write this as the basis y power of 16 and this is my basis y. And again recursively, this part or each of these parts, you can write them in the basis z power of 4 and z power of 4 and z, okay. And likewise each of these individual terms you can write as in basis w square w, w square w, and so on. Okay. So likewise here also the basis is w square w, and likewise here also the basis is w square and w. Okay. So therefore if you now just product, you just multiply, you will get the coefficient for B7 as w square z power of 4 y power of 16 and so on. Okay. So that means now if I want to do a comparison, I want to do a kind of like conversion, then I can use these products for my comparisons. I can get from these coefficients, I can get these coefficients by calculating these values. Okay. So for, if you want to calculate these values, you need to know what is your mu and n. Okay. So mu and n, once they are decided, this basis gets fixed, exactly like what we have done in the context of polynomial basis. Okay. So therefore, right, I mean let's see how the matrix looks like. So what we do is now we take the mu. So again we take the same mu as I showed to you why this choice of mu is correct. I showed to you, I think, why the choice of n is correct. Likewise you can verify why the choice of mu is correct. And once you have fixed this choice of mu and n, you get the value of y, z and w as shown here, and therefore, right, you can actually get the corresponding products in this way. Okay. So of course, like when you are doing these multiplications, you have to take like when you are doing modular reduction, you can take the AES polynomial for doing the modular reduction. Okay. So again I leave it to as an exercise to verify that indeed you get these values like 6, 4, 7, 8, all of them are in hexadecimal. That means you can elaborate them as two parts and you can write them as in binary format. Okay. Once you have got these binary equivalents, it is straightforward to write this matrix. Okay. So you can see that each of these columns, okay, so basically like what it means is that if you get this, right, you know that if I am basically multiplying this with the vector denoting B7, B6 and so on. Okay. So that means exactly that is what is in the right hand side of this matrix. So this matrix multiplies with B7 to B0 and get your result in G7 to G0. So we are basically using this matrix, mapping an element in the composite field to GF 2 power of 8. Okay. So if I call this mapping, right, as like x inverse, then that would, so or maybe x basically. So then the inverse of this mapping will take me from GF 2 power of 8 to GF 2 power of 2 whole power of 2 whole power of 2, which is the composite field representation. Okay. So you can verify that each of these columns will stand for these constants. For example, this, right, will stand for the constant 60. So you can verify that that in a straightforward manner, that this column essentially, so this part, right, stands for 6 and this stands for 0, and therefore it is nothing but 60. Okay. So likewise you can verify the other columns, okay, so which I am not going into. Okay. So now let us take a look about the comparisons, because we have derived quite a number of equations, normal basis and polynomial basis. Let us take a final look into how we can compare. Okay. So therefore what we have seen is that when we are wanting or trying to go into the compact realizations, the inversion circuits of GF 2 power of 8 requires roughly the same level of hardware. You will see, compare the two circuits, you will see there are 2 adders, 3 multipliers, 1 square and 1 scalar. So there is not much to kind of distinguish from one with the other. Likewise in GF 2 power of 2, the squaring and scaling is free in polynomial basis, but the squared is free in the normal basis. Okay. So therefore the main difference actually between the two occurs in the combined squaring and scaling operation in GF 2 power of 4. Okay. So let us take a look into that operation in more details, and here are all the possible descriptions of that, and I just enumerated the XOR count, because XOR is the most used gate in these realizations. So there are 8 choices of mu, and I told you why there are 8 choices of mu, because there are 4 roots of like irreducible polynomials like x to the power of 4 plus x cube plus 1, and likewise the other irreducible polynomials. So there are 4 roots for each of them, and you have got 8 such choices. Okay. And likewise, if you work out the cost for squaring and scaling, this is your corresponding equation. Again, I leave it to you as an exercise to verify that it is indeed the correct enumeration or correct elaboration of the equation. These are the 2 outputs. That means again this is done in the polynomial basis. So you can observe that the polynomial is written as az plus b because it's in the polynomial basis. Okay. And likewise you observe that I am trying to basically find out now that what are the costs of these operations. Okay. When you are doing these computations, again you are basically doing it in GF 2 power of you are doing it in the subfield, right. So basically you are doing it in GF 2 power of 2. So this lower field computation in GF 2 power of 2 you can again do in either polynomial basis or normal basis. Okay. And that is why, right, we have so many combinations. If you remember, we discussed in the first slide, right, about when we started this discussion, in how many ways you can write the AES S box. Okay. So you can actually do a polynomial or a normal basis representation in the lower field as well, and depending upon like the normal basis you only have one choice, but in the polynomial basis you have got 2 choices depending upon the basis. Okay. So the basis is either omega or omega square. Okay. And likewise, right, you will see that the gate counts are also varying. Okay. In the normal basis you have got another like sort of enumeration of number of gates. In particular, let me show you with one of the examples, say last one. Okay. So n square, so in this case mu is nothing but n square c plus, so c is your n square and d is 1. That means the value of mu in this case is n squared z plus 1. So if I take that, then mu is n squared z plus 1, and assuming that this is the polynomial basis for GF 2 power of 4, I mean assuming the polynomial basis for GF 2 power of 4, that means like that means as n belongs to GF 2 power of 2, if you remember I said n cube is equal to 1, further z is also a root of z squared plus z plus n. Okay. So where like n squared plus n plus 1 is equal to 0. So you can show, again I leave it to as an exercise, and you can follow it from the textbook also, that mu will satisfy this equation. That means mu is a root of the irreducible polynomial in GF 2 power of 4, which is x to the power of 4 plus x to the power of 3 plus x squared plus x plus 1. Likewise, mu can also be a root of the other irreducible polynomial, which is x to the power of 4 plus x cube plus 1, and that is why there are 8 choices of mu. Okay. One of these choice is say n squared z plus 1. Okay. So with this choice you can actually observe the squaring and scaling operation. Okay. Again, as I said, I leave it to as an exercise to verify this equation. I will just show you the enumeration here. Okay. So the enumeration works as follows. If the underlying field is normal basis, okay, that means I am talking about the last column in my table, then the squarings are free. So the squarings, right, are free in the normal basis representation, but a squaring and scaling with n equal to w and with n equal to w square both will require 1 XOR gates. Okay. And therefore, to sum up, right, these computations like a plus b will take 2 XORs, because you note that a is an element in GF2 power of 2. Okay. And that means if you want to do an addition in GF2 power of 2, you need 2 XOR gates. Okay. One for the lower bit, one for the higher bit. So you need 2 XORs here. Likewise, for this operation, also for this plus, you need 2 XORs. Okay. But what is free is the squarings are free, but the scaling is not. Okay. So whether you are doing a scaling with n square or whether you are doing a scaling with n, you need 1 XOR each, and that is why you need 2 plus 2 plus 2, that is 6 XORs. Okay. And that is exactly right what we have seen in the table. Okay. Likewise, the underlying field computation can also be done in the polynomial basis. When you are doing in the polynomial basis, you have got 2 choices, either n is equal to w or or n equal to w square. So if you take n equal to w, again a plus b and this addition can be done with 4 XORs, 2 XORs each, but the squaring and scaling with n is free. Okay. But the squaring and scaling with n squared will still need 1 XORs. So now you need 5 XORs. Okay. So therefore you see that in the lower field, if you do polynomial basis, you actually save 1 XOR. Okay. Likewise for n equal to w square. So that is exactly what we see in this table, where if you do this right, I mean the lower field computation in polynomial basis, you require 5 XORs each, whereas if you do this in normal basis, you need 6 XORs. Okay. So likewise, right, you can work out the XOR counts for squaring and scaling in normal basis, and you can see that there is a little bit of advantage when you are doing probably like the computations in normal basis. There is a another very interesting look that you can take at the inversion circuits. Okay. So here is exactly the polynomial basis inversion and the normal basis inversion neck to neck being compared. If you see that, as I said to you, if you just compute the number of computations, there is nothing much to kind of compare. It has pretty much the same number of inversions, 3. It has got the same number of XORs, same number of inversions, same number of scaling and squaring. Okay. But interestingly, you see in normal basis, all the multipliers have got shared inputs. But in polynomial basis, if you consider, for example, this pair and this pair, then they do not have shared inputs. Okay. So what is the implication of that? So if you take a look at the lower field multiplier, so the lower field multiplier is in GF2 power of 4 or GF2 power of 2, so is basically in GF2 power of 4 means it is in GF2 power of 2 whole power of 2. So then you can easily see that there is an opportunity of saving. Okay. So here I have just drawn the GF2 power of 4 multiplier, but I have drawn 2 copies of GF2 power of 4 multiplier where one argument is shared. Okay. So this is the argument that I have shared. So you can see that if I share this argument, that means this is my argument that has been shared. Then if you remember, right, this particular XOR, okay, you can actually share between the 2 computations. So that means, right, you can actually save some gates here. Okay. Likewise, you can see that there are 3 multipliers, like one, if you observe M1 and M1 dash, okay, you see that there is also one input which is shared, like this one input and this is one input, they are essentially coming from the same delta 1. So you can still save some gates over there. Okay. So in the lower field, right, you will be saving 1 gate there. Okay. So therefore for each of these computations, you will be saving 1 gate, because the lower computation will be in GF2 2. Okay. So you will be saving this XOR, means you will be saving a 1 bit XOR. Okay. Whereas in this particular field, right, it is a 2 bit XOR. So in this diagram, this is where you are saving a 2 bit XOR, but if you go down, right, and consider M1 and M1 dash, then you are saving 1 XOR. Okay. But there are 3 such cases. So you save here 1 into 3, which is 3 XORs, and therefore totally you save 3 plus 2, which is 5 XORs. Okay. So therefore, right, here you have an opportunity, if you have got shared inputs, to save 5 XORs. So now if you take a like a look back, then you will see that so if I take a look back, right, then you will see that in the previous circuit, right, you have if you now compare this circuit, right, with this circuit, that means the polynomial basis circuit with the normal basis circuit. In the normal basis circuit, you have more opportunities of sharing. Okay. Whereas in this case, you can share, but not in one case. Okay. So therefore straight away there is an advantage of 5 XORs in this computation. Okay. So therefore, it turns out that like that with all these things, right, that the normal basis representation at the top level is probably a good way to get a compact implementation. Okay, so all the hard maths pays in terms of gates. Okay, so here is a like a quick reference. You can actually, of course, go through the original paper of Canwright, which was published in Chess in 2005. But we have also tried to kind of summarize this in the textbook, which you can read and probably get more insights about how the design has been done and developed. Okay. So just to conclude, we discussed about the subfield composition in normal basis. We started with GF2 power of 8 inversions, decomposed them further into GF2 power of 4 inversions or GF2 power of 4 computational units. The GF2 power of 4 computations were then again in turn like described with respect to GF2 power of 2 blocks, which are further described in terms of GF2 computation blocks. So we discussed that squaring and scaling operations were very decisive with respect to efficiency when compared with their polynomial counterparts. And finally, the normal basis representation in GF2 power of 8 seems to be an ideal choice for compact representations of the AES S box. Okay. And in particular, right, I would also like to mention in the passing that a normal basis representation also probably gives a more fault tolerant design. Okay. But that is another story. Okay. So with this, I would like to thank you for your attention.